Hello and welcome to Submodule 1.3. This is the third submodule of Module 1 on DC analysis. For this submodule, we want to present a couple of what we would call structured circuit analysis techniques. If we recall in the previous submodule, we looked at Kirchhoff's laws, voltage dividers, current dividers, and uh, techniques that are very useful in analyzing circuits, but we would call those more ad hoc techniques. And here we're going to present two of them that rely on some of those, such as the Kirchhoff's laws and of course Ohm's law, but they're highly structured in the way that we approach the analysis of circuits. So by using these techniques, we're going to be able to calculate all currents and voltages in a circuit. Uh, these can be complex circuits that contain multiple nodes and loops, and we're going to see and define what that means specifically in the context of these techniques. And we're going to look at them via examples. That's the best way to learn these two techniques. And also, we're going to be able to know when we should be using one technique over the other. That's very important to understand that we will get the same results. It doesn't matter which technique we use. However, given the topology of a specific circuit, sometimes it is better to use one over the other. So the first technique that we're going to use is the node voltage circuit analysis, and the second one is going to be mesh analysis. And we're going to go through each one of those with an example. So let's look at nodal analysis and establish some ground rules, if you will, that we're going to rely on to make this structured technique work. First, we're going to define that the currents are positive when they flow out of a node. So that's going to be a rule that we're going to have. Also, we're going to rely on Kirchhoff's current law. So we're going to be writing current equations and equating that to zero. And if we're writing current equations and we use Ohm's law, those current equations are going to be in terms of voltages, because each current is going to be a voltage divided by a resistance. Since we're going to be having voltages as the variables in the equation, it is important that we designate a common or reference node for all those voltages, because voltages are taken with reference to another node. This is a potential differential. What works best most of the time is to designate the node that is the most common to most branches as the reference node. Usually, when people draw schematics, kind of by a natural progression of the way that schematics are drawn, it usually happens that the bottom node is the most common, and usually we see that the ground, the reference node, is the bottom of the circuit. So we'll see that once we identify the nodes that we have, we're going to write independent equations for each of those nodes. And once we manipulate those equations and put them in matrix format, we can simply apply matrix arithmetic to get the results of the voltages at each node. And of course, this would be the absolute voltages with respect to the reference node, the ground. It will not be a specific voltages across any specific component of the circuit. So let's look at this technique via an example. That's the best way to show this technique. And we see here that we have a circuit. it clearly has three independent nodes. That's where V1 is, V2, and V3. And all those node voltages are going to be referenced to this bottom node here of ground. Okay, so we have that here. And at this point, since we have identified our three nodes, let's kind of go through how we would write the three node equations in terms of voltages that are really based on Kirchhoff's current law. Remember that a current going out of the node is positive. So we can say at node 1 that we have a current going this way, and that current is going to be, since current flows from the positive voltage to the negative voltage, or from a higher voltage to a lower voltage, I can say that this current is V1 minus V2 divided by that resistance 2K. I also have this current over here, and I can say that that current is V1 minus V3 divided by 1K. And finally, I can say that I have this current, but since that is a constant current source and is flowing into the node, then it is going to be negative. So my equation for node V1 is going to be minus 4 milliamps plus V1 minus V2, that quantity, divided by 2K, plus V1 minus V3, that quantity, divided by 1K, equals 0. So that's how we are utilizing Kirchhoff's current law to write current equations in terms of voltages for each of the nodes. Now let's do the same for V2. So remember that each current is coming out of the node at each node. So now I have this current for V2, and I will say that V2 minus V1 divided by 2K, that's the first current, plus V2, that's this way here, plus V2 minus V3 divided by 4K, plus V2 minus 0, because the reference node is ground and is 0, divided by 1K. So those are my currents at V2, and they're always coming out of the node. Now we have this node, V3, so we have this current here, and that is going to be V3 minus V1 divided by 1K. Then I have this current here, so that's going to be plus 2 milliamps. And finally I have this current here, which is going to be V3 minus V2 divided by 4K. So remember that all currents are positive coming out of the node. And of course, when you have a situation where you have a constant current that you know there is no way that is going to be going out of the node, which is actually in that direction into the node, then we write it as a negative quantity. Now that I have my equations, and here I have the circuit, and essentially the equations that I verbally exposed in the previous slide. This is for node V1, this is for node V2, and this is for node V3. Once I have those, again, Kirchhoff's current law equations expressed in terms of voltages for the nodes, I can manipulate these equations to isolate each variable, each node voltage variable, and factor each of those voltages out. What I'm trying to do is get a matrix formulation of these three equations where the variables are V1, V2, and V3. So once I have that manipulation done, I can see that I have a constant here. So this is a constant times V1, a constant times V2, and a constant times V3 equals to a constant. And same with the other two equations. A constant times V1, a constant times V2, and a constant times V3 equals to another constant. So what I'm doing is manipulating each equation to have each of the node voltages multiply by a constant. And the same here for the third equation. Uh, constant times V1, constant times V2, and a constant times V3 equals a constant. Now, one thing to bring to your attention at this point is that if the currents are in milliamp and the resistance are in kilo ohms, then your voltages will be in volts, and that's just that gets yield out of Ohm's law. So if I know that, my units are milliamps for the currents, kilo ohms for the resistances, and volts for the voltage, then I can just drop the units and write my matrices. So it will simply look like this. So basically I have calculated what the constants are, and I can write it like this. So I can see that I have three independent equations with three unknowns, and I can simply use techniques of linear systems and matrices to solve for the three unknowns. So I'll write the matrix formulation, and then I can solve for my three unknowns. So the three unknowns, the vector is going to be the inverse of the coefficients matrix times this vector, and that's going to give me this result. So the voltage at node V1 is going to be 5.42A6. The voltage at V2 is going to be 2 volts, and the voltage at V3 is going to be 3.1429 volts. It is very important that you know how to use your calculator to do matrix arithmetic. Essentially this type of manipulation here, which is taking the inverse, first entering a matrix, then taking the inverse of that matrix, then entering a vector and multiplying it times the inverse of that matrix. So now that I have the voltages here, I can go back to my circuit and see what it means in terms of the actual electrical quantities that I care about in the circuit, which is perhaps not specifically the node voltages, but what I want to know is what are the voltages across the specific components of the circuit and the currents through them. So let's look again at our circuit and our results. What do I have here? I have that this voltage V1 is 5.42A6, and this voltage here is 2 volts. So I know for sure, since V1 is higher than V2, that the real current, not the nodal analysis current, which is an artifact of the analysis technique, but the real current is definitely going to be flowing this way. I also see that V1 is higher than V3, so I also know that I definitely have a current flowing this way. And since V2 is definitely higher than 0, I also have a current flowing this way. However, V3 is higher than V2. What does that mean? Well, what that means is that I have a current that is actually going this way. And that gives me the real directions for all the currents. what else do I know? If I want to know what is the actual voltage across this resistor, then I would take V3 minus V2, and that would be the actual voltage because V3 is higher than V2. So the actual voltage across this resistor is 1.429. And if I want to know the voltage across this resistor, then I would subtract V2 from V1, and I would get that actual voltage is 3.4286. And at that point, I have all the results that I want. I know everything that I want to know about the circuit in question. So that is the technique for nodal analysis. Now, let's look at a second technique, mesh analysis. First, let's define what a mesh is. Before, in the previous submodule, we mentioned what a loop was, but a mesh is a specific type of loop. It is a minimal loop that does not encircle any other loop. So we call that a mesh. And in this analysis technique, we're going to rely on Kirchhoff's voltage law to write equations for each of the meshes that are written in terms of currents, of the mesh currents. And we'll see how that works. That's going to yield independent equations, just as with the previous technique, that we're going to be able to solve using the techniques of linear systems or matrices. And once we know those mesh currents, we're going to be able to use Ohm's law to derive all the quantities that we would be interested in the circuit. Note that in the mesh analysis, the mesh current is an artifact of the analysis technique. We'll see via the example what that really means. And another point that you need to be aware of is that when we go around the mesh in the direction of the mesh current that we have defined, if we encounter a voltage, if we encounter a voltage source, then the sign for that voltage is the first sign that we encounter. So we'll see again what that means when we look at the example. So let's look at this example for our mesh analysis technique. And we have this circuit, and clearly we have three meshes. So we have this loop here that doesn't have any loop within it. We have this loop here that doesn't have any other loop in it. And we have this other mesh, again, a loop that doesn't have a loop within it. This would not be a mesh because it has two loops inside of it, and this would not be a mesh over here. This would not be a mesh, and the whole thing would not be a mesh. So we have only three meshes, again, minimal loops that don't contain any other loop, and we have defined three mesh currents. We have defined I1 for this mesh, I2 for this one, and I3 for this one. And we have defined also a direction for each of the mesh currents. Usually, I like to define them in the clockwise direction. So let's look at the equation for mesh number one, where we have defined I1. I can start at any point in the mesh as long as I come back to it. So I'm going to start here, okay? And I have a voltage here, so I encounter that plus sign first, so I'm going to write that as a positive voltage, so that's 6 volts. Then I have the next voltage here, it will be 4K times I1, so the mesh current times the resistance. So I'm just using Ohm's law and Kirchhoff's voltage law to write a mesh voltage equation in terms of the mesh currents. So that is the second term, 4K times I1. And then I come back here in the direction of the mesh current, and I say that this voltage is 6K times the following quantity, I1 minus I3, because the real current through this resistor is going to be a combination of I1 on this mesh and I3 on this adjacent mesh. But since I'm going in the direction of I1, that takes the positive sign. Since I3 is going in the opposite direction of I1, then I subtract that quantity. So the voltage in this Kirchhoff voltage equation for this resistor is going to be 6K times the quantity I1 minus I3. Now let's do the same for I2. Let's start here. So again, I encounter the negative sign first, so I'm going to write that one as minus 6 volts plus 3K times what quantity? I2 minus I3, which is going in the opposite direction, plus 9K times I2 equals 0. So we equate everything to 0 to start, because remember that we are using Kirchhoff's voltage law that says that the sum of the voltages around a loop is equal to 0. And finally, we have the equation for mesh where I3 has been defined. Let's start over here. So I'm going to say that 6K times quantity I3, positive because I'm going in the direction of I3, minus I1 on the other side, going in the opposite direction of I3, plus 12K times I3 plus 3K times quantity I3 minus I2. And those are the three equations for each of the meshes in the circuit. And remember that once you write those voltage equations around a mesh, you will equate to 0 because you are really writing Kirchhoff's voltage law equations. So these are the equations that I just spoke about. You have right there, each of them. And again, as in the previous technique, what we're going to do is isolate each current. So I end up with some constant times the unknown, the currents, equals to some other constant, so I can put it in matrix format and solve for it and get the current, the mesh current quantities. And that's what I've done here. Looks like this. Again, if the voltages are in volts and the resistances are in kilo ohms, my current results would be milliamps. And then I can drop the units and write the matrices. So here we have the matrix format for the system. And then I can do the matrix arithmetic and get my mesh currents. So mesh current I1 is equal to minus 0.6757 milliamps. Mesh current I2 is 0.4685 milliamps, and mesh current I3 is minus 0.1261. Now let's look at what this means for the actual quantities in the circuit. The real currents, remember that the mesh currents are artifacts of the analysis technique. Let's see what this means for the real currents and the voltages across the components of the circuit. And we find that by applying Ohm's law with the mesh currents that we have found. So for example, let's take what is the current through this 4K ohm resistor here. What is that current? The magnitude of that current is going to be I1. However, I1 has a negative sign that means that the real current through that resistor is in the opposite direction of the mesh current I1. So the current is going to be going in this direction. And that current is going to be 0.6757. Now let's look at the current through this 6K ohm resistor. That current is going to be the difference of the currents I1 and I3. So I inspect the results for I1 and I3. And I see that I know that there is going to be a current going in the opposite direction of I1 because that result had a negative value. So it's going to be a current on this side going this way, and that's going to be 0.6757, and another current going in the opposite way, and that is going to be 0.1261. However, I1 is greater. 0.6757 is greater than 0.1261. So the real current, the actual current, is going to be in this direction. And is going to be equal to 0.6757 minus 0.1261. Again, here for the 12K ohm is going to be I3, but it has a negative sign, so I know that that current is going to be in this direction. Now let's look at the 3K ohm over here. I have that I2 has a positive sign, so I know that the impact of I2 is going to be in the direction of the mesh current, but I3 has a negative sign, so it's going to be in the opposite direction, so it's going to be in this direction. What that means is that the current going through that resistor is going to be 0.4685 plus 0.1261, and it's going, of course, to be in that direction. And finally, for the 9K, I2 has a positive sign, so the direction was correct, and it's just going to be 0.4685 in that direction. Once I know the real total current, which is going to be the algebraic sum of the specific mesh currents, so once I have those real currents, I can just multiply times the resistance to get the voltage drop across the resistor. And that way I have all the quantities that I would care about in the circuit, essentially currents through the components and the voltages across the components. So in this submodule, we were able to look at two highly structured techniques to calculate all current and voltages in a circuit that contains multiple nodes and loops. We saw how we gainfully employed Kirchhoff's current law to perform the nodal analysis. So we wrote Kirchhoff's current equations in the nodal analysis in terms of voltages at the nodes to find those node voltages, and then use Ohm's law to find all the quantities that we would care about. Then for the mesh analysis, we gainfully employed Kirchhoff's voltage law to perform loop analysis and write those loop equations in terms of the mesh currents, and solve for the mesh currents using linear system techniques or matrices, and then use Ohm's law to find all the quantities of interest, the real currents through the components as well as the voltage drop across them. And to these examples, you were able to see when is better to use one technique over the other. Obviously, you want to minimize the number of equations in the system. So you have to look at how many nodes do you have, how many loops do you have. Sometimes it doesn't make a difference, but by minimizing the number of equations, then the analysis job is more straightforward. It is easier. So know that on the nodal analysis, you have to write one equation per node, and on the loop analysis or the mesh analysis, you have to write one equation per mesh. And by looking at the topology of the circuit, how many nodes it has or how many meshes it has, you'll be able to pick the technique that minimizes the number of equations that you have to write.